Consider a system modelled by the second order differential equation. A, B and C are given constants and f of t is a given function. F of t is often called the input signal or forcing function, and the solution y of t is called the output signal. We shall assume that the initial conditions are 0, that is, y at time 0 is 0 and y prime at time 0 is 0. Let's take the Laplace transform of this differential equation. Now a is a constant, so by linearity we can leave that to one side and get L of the second derivative. So in general, here is L of the second derivative of y with respect to time. That's s squared times big Y of s, where big Y is the Laplace transform of little y. Now we're given that y prime is 0 and y of 0 are 0, so we just end up at s squared times big Y of s. So that's this first term here, with a included, as squared times big Y of s. When we get L of b times dy dt, we leave the b to one side by linearity, so we get L of dy dt, which is s times big Y of s minus little y is 0. That's 0, so we just end up with bs times big Y of s. And finally, we have L of c times y. Well, that's c times L of y, and L of y is big Y, so we get c times big Y of s. And we're calling L of little f of t big F of s. Now, the transfer function of a system is defined to be the ratio of the Laplace transform of the output signal, which is big Y of s, to the Laplace transform of the input signal, which is big F of s, with the initial conditions as 0. So for this case, we see that Y of s is F of s divided by as squared plus bs plus c, and we need to divide that by F of s. So we get 1 over as squared plus bs plus c. So h of s is our transfer function. In the special case in which the input signal is the delta function, we have big F of s equals 1. Now we saw that in a previous video. Let's just look at that again. Here's the definition of the Laplace transform of delta t. We multiply by e to the minus st and we integrate from 0 to infinity with respect to time. Now, we saw the so-called shifting property of the delta function in a previous video. Let's just see what's going on here again. Here's a sketch of e to the minus st. When t is 0, function has value 1. Delta t is a spike at 0, and it just picks out the value of the function e to the minus st at 0. So it just sifts out that value, which is 1. So all of this integral is just equal to 1. So if f of s is 1, we see that the transfer function h of s is equal to y of s. We call the solution to the differential equation, just in this special case, the unit impulse response function, and denoted by little h of t times u of t. So L inverse of big Y is the same as L inverse of big H, which is little h. Now in the general case, big Y of s is big H times big F. To go from y to little y, we get L inverse, of course. But we know from the convolution theorem that L inverse of h times f is little h convolved with little f. Let's get the impulse response function, little h of t, to this system. The initial conditions have to be 0, and we imagine that on the right hand side we have a delta function. So when we get L of the delta function, we just get 1. When we get L of the left hand side, we saw before, we get as squared plus bs plus c, where a, b and c are the coefficients, which are constants. A is the coefficient of the second derivative, which is 1. B is the coefficient of the first derivative, which is actually 0, so we have no s term. And c is the coefficient of y, c is 4. Notice that for the system, big H of s does not depend on big F of s. Big F of s cancels out. So for a second order system with constant coefficients, we always get a function of this form. Now we are interested in little y of t, the solution to this differential equation here. That's the one with e to the minus t on the right hand side. So we go back to this that we saw earlier, using the convolution theorem. H of s doesn't depend on what f of s is, so we found big H of s. So to find the solution to our problem, we need to get little h, that's the inverse transform of big H. And we need to get little f, that's the inverse transform of big F. And big F Well, little f is actually e to the minus t. So this is what we need to calculate. What is little h? Well, that's inverse transform of big H. We have a function of the form a over s squared plus a squared. Here it is. We see that a squared is 4, so a must be 2. So we want 2 on top, so we stick a 2 on top here, and then we have to divide by 2, so that's where this half comes from. So we've a half inverse transform of 2 over s squared plus 4. Well, that's sine of 2t. We said a equal to 2. So now we convolve h with e to the minus t. So we get h at t minus x. So as a reminder, here is the general formula for convolution. We take the first function, h in this case, get it at t minus x. So we have to get a half sine 2t at t minus x, and then get the second function at x. The second function is e to the minus t. So we have e to the minus x. And to actually do this integral, we have to integrate by parts twice, which I won't bother doing. Now, if you don't want to do this integral by hand, of course, you can go to a website like Wolfram Alpha and just type this in here. So we're integrating from x equals 0 to t. So we're integrating this thing with respect to x. Let's use the transfer function approach to solve the equation dx dt minus 4x equals sine of t with initial condition x of 0 equal to 0. So we get the Laplace transform of the differential equation. The Laplace transform of the first derivative dx dt is little s big X of s minus little x at 0, where big X is L of little x. And we have it here again. Using linearity, we take out minus 4. We need to get L of sine of t. Well, we can look that up. We use this rule with a equal to 1, so we get 1 over s squared plus 1 squared. Now we're given that little x of 0 is 0, so we can forget about that term. We factorize out big X of s and divide across by what we get. So that's little s minus 4. Now this is the approach that we took before. But using the transfer function approach, I should have just put delta t here. And we know the Laplace transform of the delta function is 1. Now, in previous videos we saw how to use this approach. We wrote down the partial fractions. We broke this into 2 fractions with denominators s squared plus 1 and s minus 4. So I won't do it that way. Just go back to what we have here. So this thing here is now 1 using the transfer function approach. So big X of s is going to be 1 over s minus 4. As a reminder of the transfer function, big H of s is the output big X of s divided by the input big F of s, where big F of s is equal to 1 in this case, if the input is delta t. So since big F of s is 1, we just have x of s divided by 1. Well, that's just x of s. So this up here is just h of s. So we need little h of t, so we get the inverse transform of 1 over s minus 4. Well, we just looked that up. It's a function of the form 1 over s plus a with a equal to minus 4, so we get e to the minus 4 or e to the plus 4t. From the previous part, as we saw for the previous example, little y of t, that's the solution to this equation here, well, it's little x in this case, is given by h star f, where h is e to the 4t, and little f of t is right hand side here, sine of t. So we have to get the convolution of these two functions. So to do that, we have to integrate from 0 to t. The first function h at t minus x. Well, the first function is e to the 4t ut, so we have to get that at t minus x. And we can put in the u if we like, I won't bother. And then the second function at x, so we want sine of x. Now we have a product of functions here. We use integration by parts. So which of these functions do we call u? Well, we use the rule LIATE, and we have a trigonometric function here, sine of x, and the exponential function is e to the 4 times t minus x. So t comes before e in this rule, so we set u equal to sine of x. That means that du dx is cos x, and dv then is the rest of this integral. It's e to the 4 times t minus x dx. So we have to get v from that, so we have to integrate this with respect to x. So it's an exponential, so we get it back again. But then we must divide by the coefficient of x, so that when we differentiate by the chain rule we get this back. So the coefficient of x is minus 4. T is treated as a constant. So we multiply u by v, so we multiply sine of x by e to the 4 times t minus x over minus 4. So that's what we have here. And you can see that e to the 4t has been factorized out, so that comes out. And our limits are from 0 to t. That's our limits on u times v. Then we have the integral of v times du. Well, v is this thing here, e to the minus 4x, but e to the 4t has been factorized out of this as well, so that goes out to the front. That's treated as a constant. We're integrating with respect to x, so we get e to the minus 4x in here, and we have the minus 4 underneath, and that's multiplied by du. Du is cos x dx. Okay, we stick the upper limit t in here for x, so we get minus sine t over 4 times e to the minus 4t. And then we plug 0 in. Well, if we plug 0 in, the sine of 0 is 0, so we just get 0. Now, we have to use integration by parts here again. We let u equal the exponential term. So du is e to the minus 4x over minus 4, just like we saw before. That's du. And, well, the du appears over here. We have integral of v times du. So dv is cos x times dx. So the integral of that is sine x. So sine x is v. So here's v. So here's the integral of v du. V is sine x. Du is the derivative of v to the minus 4x. Well, let's just write out this more carefully. I'll go through this in detail. So if we let u equal to cos x, the trigonometric function is cos x, we get du equals minus sine x dx. So we want minus sine x, that should be dx there. dv is the rest of the integral, which is e to the minus 4x dx. Integrating that, we get minus a quarter e to the minus 4x. So we have to multiply u by v. So we get cos x times minus a quarter e to the minus 4x. That's this here, from 0 to t. Plus a quarter has been taken out here, and over here we have the integral of v times du. So that's minus a quarter e to the minus 4x times du, which is minus sine x dx. So we multiply these two together. The two minuses give a plus, so we just have the minus sign here for the rule for integration by parts. Okay, so I've written out the left hand side here by taking e to the 4t out. So e to the 4t is just a constant here when we're integrating with respect to x. Okay, so that's just this written down here. And on the right hand side, well, I've written down this line here, the first part of it, but I plugged in the limits here. Plug the upper limit t in for x, so we get minus cos t over 4 e to the minus 4t. Then we have a minus sign, and this again, so we have minus minus or plus cos naught over 4 e to the naught. Well, the cos of naught is 1, e to the naught is 1, so we get plus a quarter. And over here I've factored minus a quarter out of this integral, so we end up with this. But notice now that this integral is the same as this one here, so we can call this I, shorthand for this. We could then solve for I, gather the two of them together, and from I we can get what we want by multiplying it by e to the 4t. That's what we want. Anyway, if we do all that, we'll get this for our result.